Well, we'll go ahead and get started.
Maybe these two. Go down.
Well, we'll get started here. Should have. Compost bedded pack management. We've already had a lot of information on this. I felt my role might be to try to give some science to why these systems behave the way they do and so on. So what I'm going to do is give you some information in that regards. Of course, with compost bedded packs, we know it's a loose housing system. We know that generally you'll end up with 3 to 4 feet of material in that barn. We design it that way. Mechanical stirring is very beneficial. We've already had a lot of discussion on that in terms of the impact on the animal from the cow comfort, health, and the management side of it. One of the things that in Ohio, when we looked at 4 different farms, and it's already been discussed, I think, with Kentucky and so on, they talk about 100 square feet per animal, 110 square feet per animal, if I recall correctly. In Ohio, what we found was that the barns were anywhere from 75 up to about 90 square feet per animal. We got to remember that not all people have 1,400-pound Holstein cows. That if they're Jersey cows, you may use a different. You may want that different number than that, depending on the animals. The side walls, in terms of containing the bedded pack area, or the concrete wall, I should say. Side wall in our barns were about 16 feet. Smallest or the lowest was the 14-foot side wall. Sawdust was the main bedding material. But there was several instances where the farmer needed to use other materials besides sawdust because it was not available. And they found that if they used straw, it did not work very well at all. Our recommendation would be to chop the straw and to alternate straw with sawdust. If you see you're going to have a problem with having enough sawdust through the whole year, then try to work into a management scheme where you alternate between the sawdust and the straw, but chop the straw as well.
How fine to chop?
Probably 2 to 4 inches, something of that sort. And I don't know if Ling Ying will have any more information on that or not. Stirring frequency, it's been emphasized over and over again today. You got to go 2 times a day. We talk about the feed alleys as well. Scraping those several times a day can have an impact on dragging manure into the bedded pack area. And then clean out of your bedded pack several times a year. It was recommended to leave some of that bedded pack in there. I think time of year will dictate a little bit whether you would want to leave that bedded pack in there or not, and just how wet that bedded pack material is when you're hauling it out of the barn. If it's relatively dry yet, so on, it would make sense to recycle some of that in order to give you that bed depth. Is that real critical in terms of the growth of the microorganisms? In all the compost studies we ever did, we found that the minute we threw some manure into any material we were trying to compost, we had an explosion of population. And the key was if you came up to the right moisture levels and so on, that manure itself did a good job of inoculating. So I think recycling of bedding of 1 foot or whatever, that does detract from the total volume space you have available. Of course, it is breaking down over time. So that is something to consider. Time of year and the moisture content of the material you might want to recycle. What are some of the composting fundamentals? Composting is done by bacteria and fungi mostly. And we talk about good bacteria, bad bacteria, I guess, in terms of pathogens. But it is the bacteria primarily in these compost bedded pack areas that's doing the work for us. It's not the fungi. Moisture levels. We need to be above about 45% moisture levels for the bacteria really to perform and do composting. The bacteria require a biofilm around any of the material in order for them to survive and do the job of breaking down that material and releasing heat. Fungi actually can operate at about 15% moisture level. And a good example of that is grain itself. You store grain above 15%, temperature goes up to 55 degrees Fahrenheit or above, it'll start to spoil on you in almost all cases. But it's not the fungi that we're really interested in terms of these bedded packs. It's the bacteria. Oxygen levels, we like to see about 5% oxygen levels or above in that 18 inches or so that we're doing the stirring in. And it's already been mentioned, if you were to take a look at oxygen gradients, you'll see that it's near ambient right at the surface, and it will drop down to where you get into that bottom layer where you're not stirring. But that's very critical if you don't want to have odors generated in these systems. Aerobic organisms, the bacteria that operate aerobically generally do not produce offensive odors. Temperatures. We want to see our beds come up above 100 degrees Fahrenheit. It's already been mentioned about achieving this 120, 130, and so on. We know that in composting, if we get above 130 degrees Fahrenheit for more than 3 days, we see a very significant drop in pathogenic organisms. I think some of the discussion that's already been presented here today talked about some of the issues with pathogens and so on, and there's still some unknowns in that regard. The other thing we found in composting is that having other microflora in there, other bacteria in there, serve as a competition against pathogenic organisms. Compost, when we use it for control of plant diseases, one of the mechanisms that works there is that they're so competitive that if there's a highly biodegradable food base, they will attack and eat that up quicker than the pathogens can. And so the pathogens lose their ability to explode. If you have, take compost, put it into a potting mix, want to grow a plant in there, the pathogenic organisms will not outcompete the non-pathogenic organisms. How might that apply to a cow? Mastitis, and correct me on this, those of you that are the animal scientists, but mastitis, we generally think about a cow teat and the opening on the cow teat and the leaking of some milk out and so on. That milk is a food base for pathogenic organisms. If there's other bacteria that are non-pathogenic, and this is a hypothesis, I'm waiting for the animals, veterinarians and others to maybe to put data to this, but if you have other bacteria in there that are non-pathogenic, they're going to compete for that food base. And the concept is that that will reduce the prevalence then of mastitis getting into the teat of the animal. Again, maybe that'll be part of the discussion here, and we can ask some of the veterinarians about that idea. In terms of composting, the temperature rise in composting, when you first put your bed out there, you're not going to see immediate temperature rise. It's going to take a while until the moisture builds up. Again, we've discussed that already. We need to get up into the 45, 50% moisture range for that to happen. I'm going to give you a little bit on some basic concepts. Decomposition. Pardon me. How much heat energy is actually generated when material decomposes? It's about 8,000 BTUs of heat energy. Now, how can you relate that? Well, you think about a gallon of propane. It's a little over 90,000 BTUs of heat energy. So if you lose 11 pounds of dry matter, you've got the equivalent heat you would get if you burnt a gallon of propane. So we do get the heat from the breakdown. Decomposition. This hasn't really been mentioned, but when material decomposes, organic material decomposes, you will produce about a half pound of water for every pound that disappears. So you put the sawdust in there, it breaks down. It's generating water. You don't think about that. All you think about is the heat that's being generated. But it does generate water. The thing is, when you do the calculations, and what we have found from our studies on composting, is if we can get airflow into our compost, the heat that's generated, we can remove 4 to 6 pounds of water per pound of the dry matter that decomposes. So, yes, it produces some water when it decomposes, but that heat energy more than takes care of that problem if you have airflow into the system. Now, I'm going to try to expand a little bit on these concepts as we move along and just show you why it's so critical to stir that pile and get airflow in and out of it. Management fundamental, water and bedding, up to 65%, some cases 70% moisture levels. Bedding is non-sticking. Now, I think based on what Kentucky and Tennessee is telling us, I've got these numbers too high. We probably need to keep those numbers 60%, 55%. And I think that would be probably the more appropriate numbers there. I've went with the 70% because I knew from some of our composting studies, so on, we could take certain materials, organic materials, and it would hold 70% moisture and still not cause a problem. So each of your bedding materials is going to have a little bit different characteristics. But based upon them, they've studied 60 farms now and so on. Based upon their data, 55, 60% moisture is probably the upper limits that you would have to stay with in order for it not to be sticking to the animal and so on. The key is there is an upper limit. How much moisture can bedding hold? There's a formula here. We're not going to try to use that formula and so on, but at least not as far as me showing you the use of it, except in a table. But bedding can only hold so much moisture. And it's really not a whole lot if we don't take account of the composting effect of evaporating water out of the system. I mentioned before about the fact that compost produces about 8,000 BTUs per pound of dry matter that disappears. Water takes about 1,050 BTUs to evaporate 1 pound of water. And so when you do the numbers, you would think you could come up with 6 to 7 pounds of water during evaporation. But in all of our compost studies, and in particular this was with dairy manure composting it with sawdust in a windrow, we found that as 1 pound of biomass disappeared, we were getting 4 pounds of water evaporated if air exchange occurred. And that is where the importance of stirring comes in. Also, just surface drying and air moving over the surface becomes very critical. So we want air movement into and out of the building. Again, that needs to have some control on that so that we don't over cool bedding material. This is just an illustration here showing how after stirring we see the moisture coming up out of this bedded pack. Water loss with air exchange. I wanted to say, from an engineering perspective, why does stirring work? And what happens if you don't stir? If we take some bedding material, and I use the final moisture 70%, ideally I would go back and run this maybe at 60%. But for purposes of illustration, the numbers and relative ideas turn out to be the same. If we start with bedding material at about 30% moisture, allow it to go up to 70% moisture, the bedding will take up 1.33 pounds of water per pound of bedding material. If you don't stir it and you lose 25% dry matter loss, that number actually decreases to about 0.84 pounds of water per pound of material you added to the bed. And that's because the bedding, without stirring, the water stays in the system and builds up on you. and it actually decreases then the advantage of using bedding. But with stirring, with this 25% dry matter loss, we increase significantly then the amount of moisture that will come out of the system up to 1.64 from the 1.33. And that happens because now we're taking advantage of the heat energy that was generated. It evaporated the water, and by stirring it and getting airflow through it, it took that evaporated water out of the system. If you didn't stir it, the water would stay in the system and build up your moisture level. Somebody mentioned about moisture or production per day. I went back to the 604 bulletin. This would be for a 1,400 pound cow. If this is a Jersey cow, of course, these numbers would be quite different. But at 90 pounds of milk per day, you're producing about 153 pounds of manure. And about 135 pounds of that manure is water. If she's producing 50 pounds a day, you're getting 113 pounds of water. And if you had a heifer, 750 pounds, you get about 57 pounds of water per day. I went ahead and did calculations where I said, how much bedding will we need to absorb water from manure to achieve a 70% moisture in the manure and bedding? And came up with a table. You have that table. What I want to do is I'm going to jump to the next slide and just illustrate to you what it takes based upon, this is bedding required for the cattle to maintain 70% moisture level in the manure and bedding. And it's based on that 25% dry matter loss for this high producing cow, producing 160 pounds a day of manure. And the purpose of this table is to look at this issue of designing your facility so that the cow does more defecation in other areas than the bedded pack area. If you think back, or if you go back to look at the slides that Kentucky first gentleman was presenting, he showed a layout of the building with the water location and the feed bunk location. And I know Mike Brugger will talk about building design this afternoon. But those become very key issues in terms of where is the cow doing the defecation. If she's out on pasture or anything else. It's obvious to everybody, but it becomes critical when you look about how much bedding do I really need in terms of the operation of the system. If 25% of the manure ends up in the bedded pack area, and we have bedding coming in at 10% moisture, it would take about 10 pounds a day. If she's putting 75% of her manure in the bedded pack area, it's going to jump up 3 times, of course, to 30 pounds a day. And then the other factor of this table, I just wanted to point out, bedding moisture can have a very significant impact when you go out there to buy a truckload of, semi-truckload, how much material are you going to need? So, all I'm trying to do here in my presentation is to reinforce 2 very important concepts. Stirring. If you don't stir, you're actually going to see moisture accumulating faster than what the bedding would say you should. But if you do stir, you're going to see a lot more moisture coming out of the system, which has already been well documented. And then design of the system and management of the system in terms of where you put your water, where you put the feed bunk, and so on, trying to change the cow behavior to such that you have less of the manure being defecated right in the bedded pack area. It's going to be very important, especially when you get into situations where you have limited bedding materials available, like several of the farms here in our state have been encountering. Different systems. This is just a field cultivator being used. This actually has both, of course, Jerseys and Holsteins in the operation. The chisel plow will give you much deeper depth opportunities. And in this particular barn case, you see the feeding system over here, the bedded pack area over on this side. And they already talked about fans. This particular barn using the Axial-Flow fans, feed alley, I can't say whether there were dead zones in this barn or not. Now what happened? Did it lock up on me? Looks like I got it locked up.
Does it go back?
Doesn't look like there's any wall separating the feed alley.
In this barn, there wasn't. And that's in many cases, that's a disadvantage. Did you get it to go?
I hit escape, so.
So we'll go ahead and I'll try to. One of the things I wanted to look at with terms of the Ohio study was these ratios of NP and K, in terms of the numbers that we got in our study. Again, this is very much impacted by how long you leave the material in there. If you left that in there for 3 years, you're going to get a lot different number than if you take it out every 6 months. But if you look at what came out of our study, we had 17, for a ton of material, 65% moisture coming out of the system. It had about 17 pounds of nitrogen, 7 pounds of P2O5, and 14 pounds of K2O. If you looked at that from the standpoint of using it on a corn ground, you'd get about, that ratio would work for the phosphorus and the potassium, but you would come up short on the nitrogen. It would only supply about half the nitrogen you need. So for this particular material, applying it, you definitely would end up needing to apply additional nitrogen to the corn. Spacing requirements. These are our recommendations that we came away with for Ohio. 70 to 90 square feet for 900 to 1,400 pound cows. Concrete walls, 3 to 4 feet to hold 6 to 12 months. A feed alley, 12 feet wide, separated from the pack. Waters in the feed alley. Ventilation, we want 14 to 16 foot sidewalls. Bedding management, fine dry sawdust, and if you supplement with straw, chop it and alternate with the sawdust. Initial depths, 12 to 18 inches, similar to what others have talked about. And it says include bedding from clean out to inoculate for composting. The point I was making is generally that I don't think that's necessary, but there are certain times of the year, especially if you're talking about late fall to reestablish your bed and everything, recycling some of the bedding material would make sense. But if you're doing it at another time of the year, it may not make good sense. Additions, add 1 to 2 inches when bedding sticks to cows after lying down. It's already been mentioned, you don't want to get to that point. You want to do it ahead of time. And experience will tell you how to manage that. And of course, 2 times a day, minimum of 10 to 12 inches. Feed alley, scrape twice a day, separate storage. Pack, remove every 6 to 12 months. Others, pasture, definitely, we know if the cow's on pasture and so on, it's going to adjust the frequency of stirring, bedding, alley scraping. And land application, shouldn't be an issue at all. If the CN ratio exceeds 20 to 1, why we may see some, if you apply it to a growing crop, of course, it would probably tie up some nitrogen.